Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I wish to discuss about the question bank questions on crystal structures. So, here the first problem. Calculate the number of atoms per unit cell of a metal with lattice parameter 2.9 angstroms, given molecular weight 55.85 kilogram per meter cube. Density is 7,870 kilogram per meter cube, and Avogadro number is 6.023 into 10 power 26 kilo per mole. So this comes under the Bloom's taxonomy level of coupling. So the course outcome is CO1. So let's see again the problem. So here in the problem, we have to calculate the number of atoms per unit cell of a metal. So calculate the number of atoms per unit cell of a metal with lattice parameter, which has been given 2.9 angstroms, and the molecular weight of that atom is 55.85 kilogram per meter cube. The density also mentioned 7,870 kilogram per meter cube, and Avogadro number 6.023 into 10 power 26 kilo per mole. So here the data which have been given is written here. So the lattice parameter A is equals to 2.9 angstroms. So converted into meters, 2.9 into 10 power minus 10 meters. And then molecular weight 55.85 kilogram per meter cube. Density rho is equals to 7,870 kilogram per meter cube. And Avogadro number, which is denoted with Na, that is equals to 6.023 into 10 power 26 kilo per mole. So here we need to calculate the number of atoms per unit cell of a metal. So need to calculate number of atoms per unit cell of a metal. So number of atoms is mentioned with N. So N is equals to how many atoms are there. This one we need to calculate. So for that we are going to take the formula. So the formula for A is equals to Nm by rho into Na whole power 1 by 3. So from this we can derive N. So N is equals to rho into Na A cube by M. So M is the molecular weight, Na is the Avogadro's number, A is the lattice parameter, and rho is the density, N is the number of atoms. So in this, N is the number of atoms per unit cell, rho is the density, Na is Avogadro's number, A is the lattice parameter, and M is the molecular weight. So let's substituting the values of rho. Rho is 7,870 kilogram per meter cube, and The Avogadro number 6.023 into 10 power 26. And then lattice parameter A is 2.9. That is n is equals to 7870 into 6.023 into 10 power 26 into 2.9 into 10 power minus 10 whole cube divided by m. M is 55.85 kilogram per meter cube. So this value becomes 2.06. It is equal to 2. That is, the number of atoms per unit cell is 2. Next problem. Chromium has a BCC structure. Its atomic radius is 0.1249 nanometer. Calculate the free volume per unit cell. So this is also a taxonomy level of apply. So chromium has a BCC structure. BCC means body centered cubic. Body centered cubic structure. So BCC structure means that body centered cubic structure. So its atomic radius or is equals to 0.1249 nanometers. So this one will be converted into meters. So 0.1249 into 10 power minus 9. Minus 9 meters. So volume per unit cell of BCC structure. So the free volume per unit cell of BCC structure is 0.32 into 0.32 into a cube. Free volume per unit cell of BCC is equals to 0.32 into a cube. So because here in the problem, so chromium has BCC structure and the atomic radius have been given 0.1249 nanometers. But we need to calculate the free volume per unit cell. So how much free space is there in the unit cell of chromium which has BCC structure. So in BCC structure we know that the free volume is 0.32 into a cube. So this much of space will be free in the BCC structure. So as it has 68% of packing factor. So atoms are filled in the cube is 68%. So remaining 32 is free space. So that free volume per unit cell of BCC structure is 0.32 into the volume of the cube. So what is the A here? So in this, what is A? A we need to calculate. So relation between R and A, that is R we have. So to know that lattice parameter, what is the relation between R and A in BCC structure? So in BCC structure, in BCC, R is equals to radius R is equals to root 3A by 4. So here A is equals to 4R by root 3. So substitute 4 into R is 0.1249 into 10 power minus 9 divided by root 3. So this value becomes 2.884 into 10 power minus 10 meters. So this is the A value. A in the sense lattice parameter. So here A is, so free volume per unit cell, this A, so A is 2.884 into 10 power minus 10. So that to calculate the free volume, 0.32 into A cube. So 0.32 into A is the 2.884 into 10 power minus 10 whole cube. So that is equals to 7.676 into 10 power minus 30 meter cube. And so this is the free volume which is in the chromium BCC structure. So copper has a FCC structure. So FCC is face center cube. So face center cubic structure. So copper has FCC structure and the atomic radius is 1.278 angstroms. Calculate the density of copper crystal. Given atomic weight of copper is 63.5. So it is applying level of Bloom's taxonomy. So copper has FCC structure. The atomic radius of this is 1.278 angstroms. So atomic radius R is equals to 1.278 angstroms. And we need to calculate the density of copper crystal. And atomic weight has been given. So atomic weight of copper, capital M, is equals to 63.5. So here we need to calculate the density. So density of copper crystal. So we know that Na, because so the relation between R and A in FCC is R is equals to A by 2 root 2. So A, we don't know. So A is equals to 2 root 2 into R. So 2 root 2 into 1.278 into 10 power minus 9. 10 power minus 10 meters. So if we won't change this one, keep it in angstroms. So then we will get, if we are not changing, keeping in angstroms, so that we should not write into 10 power minus 10. So A is equals to 2 root 2 into 1.278 angstroms. So the value is A is equals to 3.614 angstroms. So we know that Avogadro number 6.023 into 10 power 26 kilo per mole, and the formula to calculate the density. So from the formula, A is equals to Nm by rho into Na power 1 by 3, 3. 1 by 3. So from this, rho is equals to Nm by Na AQ. So let's substitute. Rho is equals to, so here we can get that the value rho is equals to 8.92 into 10 power 3. 10 power 3 kilogram per meter cube. Next problem, show that in a simple cubic lattice, the separation between successive lattice planes 100, 110, 111 are in the ratio 1 is to 0.71 is to 0.58. So this is understanding level of Bloom's taxonomy. So here in this problem, so we need to calculate, or we need to show the simple cubic lattice, the separation between successive planes of 100, 110, 111 or in the ratio of 1 is to 0.71 is to 0.58. So let's see that planes or lattice planes are 100, 110, 111. So lattice, simple cubic. This is belongs to simple cubic lattice. So that we need to calculate first, then we'll show the ratio. So separation between successive planes. So that is D we need to calculate. So separation between successive lattice planes. So what is the separation between the two successive planes? If the structure is being like this, so what is the separation to this plane and this plane? Successive planes. So that we know that formula for the interplanar spacing or separation between the lattice planes, interplanar spacing, D is equals to A by root of H square plus K square plus L square. So we need to calculate for these three lattice planes. So take the first plane. So interplanar spacing of 100 plane is equals to A by root of, this is H, K and L. So 1 square plus 0 square plus 0 square. It is equals to A by root 1 is equals to A. So next this another successive plane of this 100 is 110. So A by H, K, L root of 1 square plus 1 square plus 0 square. So it is equals to A by root 2. Next, the successive plane to this one, D111 is equals to A by root of 1 square plus 1 square plus 1 square. So A by root 3. So the ratio of the three successive planes, that is D100 is to D110 is to D111 is equals to A is to A by root 2 A by root 3. So when taking this the ratio 1 is to 1 by root 2, 1 by root 3. So calculating this, we'll get 1 is to 0.707 means 0.71. So is to 0.577. So this can be written as simplifying this, the plane becomes D100, D110, D111 is equals to 1 is to 0.707 is nothing but 0.71 is to 0.577 can write as 0.58. So this is that. Find the Miller indices of a set of parallel planes which makes intercepts in the ratio 3a is to 4b on the x and y axis and are parallel to z axis. A, B, C being primitive vectors of the lattice. So applying level of Bloom's taxonomy. So here we have to find the Miller indices of a set of parallel planes. So which makes interceptions in the ratio of 3a is to 4b on the x and y axis and are parallel to z axis. A, B, C being primitive vectors of the lattice. So let's write the data given. So interceptions of 3a is to 4b. If plane is parallel to axis, then the corresponding intercept is infinity. So if the plane is parallel to axis, so here the interception on x and y axis or 3a is to 4b, but they are parallel to z axis. So they are parallel to z axis means that the interception is infinity in the z axis. Infinity is, the interception on z axis is infinity because the plane is parallel. So that the interception on x axis. So solution is interception on x axis is equals to 3a. Interception on y axis is 4b. But the interception on z axis is infinity because x and y axis have the intercepts and these are parallel to z axis, so that no interception on z axis, so that it is infinity. Interception on z axis is infinity. So therefore we have to write the multiple of lattice parameter. So P is to Q is to R is equals to 3A is to 4B is to infinity. So take the multiples, that is H is to K is to L is equals to 1 by P, 1 by Q, 1 by R, 1 by R. So that is equals to 1 by 3, 1 by 4, 1 by infinity. So this we need to make it the integer number so that it becomes 430. So take the LCM. So we have to take the LCM. So first in the Miller indices we have to take the intercepts. First we need to take the interceptions on the axis. So take the intercepts with multiples of lattice parameters and then take the multiple of lattice parameter and take the reciprocal and then convert it into integer by taking the LCM, then put it in the parenthesis. So these are the steps which is to find Miller indices. So first we took the intercepts with the multiple of lattice parameters. Then we took that multiples of lattice parameters, that is 3:4:infinity. Then take the reciprocal so that we'll get 1/3:1/4:1/infinity. So take the LCM of this one. So when taking the LCM, we'll get 12. So that 3 4s. So 4 3 is 3. So this one 0. So 4 3 0. So keep it in closed brackets. So we'll get Miller indices 4 3 0. 4 3 0. This is the Miller indices of a set of parallel planes which intercepts in the ratio 3a:4b on x and y and are parallel to z axis. Next, in a triclinic crystal, a lattice plane makes intercepts of lengths a, 2b and -3c/2. Find the Miller indices of the plane. So it is understanding level. Okay. So the given data is first we need to. So here we have to find the Miller indices. So Miller indices already in the previous slide have written what are the steps to find the Miller indices. So first we have to write the intercepts with multiple of lattice parameters. So intercepts on x and y, x, y and z planes or a, intercepts on z axis -3c/2. Now we have to write it multiple of lattice parameter. So PQR is equals to PQR is equals to 1, 2 and -3/2. Now is equals to take the reciprocal. So 1/1, 1/2 and then 1/-3/2. So here we can write we can write 1:1/2 and 2/3. So that we can write this 6, 3 - 4. So keep it in closed brackets. We'll get 6, 3 for inversion. So for the negative, we have to write the bar in the Miller indices. So 634 bar is the Miller indices of this triclinic crystal. Next one, applying level of Bloom's taxonomy problem. Determine the spacing between 100 planes, 110 planes and 111 planes in a sodium crystal, sodium chloride crystal having the lattice constant A is equals to 5.64 angstroms. So we have to determine the spacing between the planes. So the planes are 100, 110, 111 plane. So lattice constant is A is equals to 5.64 angstroms. So need to calculate interplanar spacing. D. So the formula which we are going to use is interplanar spacing. D is equals to A by root of h square plus k square plus l square. So first we'll find 100 plane. So it is equals to, this is h, k and l. So A is 5.64 angstroms divided by root of h is 1 square plus 0 square plus 0 square. So it is equals to 5.64 by root 1 is equals to 5.64 angstroms. Next, another one, 110 plane. So 5.64 divided by root of 1 square plus 1 square plus 0 square is equals to root 2. So it is equals to 3.988 angstroms. Next one, D11 plane. So 5.64 divided by root of 1 square plus 1 square plus 1 square. So 5.64 divided by root 3, that is equals to 3.256 angstroms. So these are the interplanar spacing between these three planes of a sodium chloride crystal which have the lattice constant 5.64 angstroms. Next, the distance between 110 planes in BCC is 0.203 nanometers. Calculate size of unit cell, radius of atom. So this comes under applying level. So the given data, the plane is 110. So distance of this 110 planes in BCC is 0.203 nanometers. So spacing in BCC, spacing, interplanar spacing in BCC is D is equals to 0.203 nanometers. So we need to calculate the size of unit cell. Size of the unit cell. So size of the unit cell. So it is BCC, so that it is a cube. So cube has the size that is volume A cube. So A cube we need to find. then a radius of the atom, or we need to calculate. So for that, first by using the D and A, we can find A value. So D and the plane, we can find the A. So the formula which we are using is interplanar spacing. D is equals to A by root of h square plus k square plus l square. So from this, A is equals to D into root of h square plus k square plus l square. So it is equals to D is 0.203 into root of 1 square plus 1 square plus 0 square. So 0.203 root 1 plus 1 is 2. So this is the A value. So this A becomes, A is equals to, when 0.203 into root 2, it comes, A is equals to 0.287 nanometers. So this is the A value. So but we have to find the size of the unit cell, and we have to find the radius of the atom. So in BCC structure, the relation between R and A is R is equals to root 3A by 4. In BCC, R is equals to root 3A by 4. So let's substitute root 3 into 0.287 divided by 4. So R is equals to 0.1242 nanometer. This is the atomic radius. Atomic radius is R is equals to 0.1242 nanometer. But size of the unit cell. So as it is cube, body centered cubic structure, so the volume of the unit cell is nothing but size of the unit cell. So that is A cube. A cube is equals to 0.287 nanometers. So A is equals to 0.287 nanometers. So 0.287 into 10 power minus 9 meters. Okay, so when taking A cube, so 0.278 into 10 power minus 9 whole cube meter cube. So it would come 23.63 into 10 power minus 30 meter cube. This is the size of the unit cell which have the BCC structure. So first we have to find the A value by using the interplanar spacing, because distance have been given and then plane also mentioned. So that from the formula D is equals to A by root of h square plus k square plus n square, we found A value, and then as we have to calculate the radius of atom, so that in BCC structure the relation between R and A, radius of the atom, and the A value is R is equals to root 3A by 4. So substituting the A value, we got the radius of the atom. So R is equals to 0.1242 nanometers. So this is the radius of the atom. Then the second thing, we have to find the size of the unit cell. So as it is a BCC structure, so volume of the unit cell is A cube. So that is nothing but size of the unit cell. So A cube is equals to 0.287 into 10 power minus 9 whole cube. So we'll get 23.63 into 10 power minus 30 meter cube. Then another one, a copper has FCC structure with atomic radius 0.1278 nanometers. Calculate the interplanar spacing for 111 and 321 planes. So applying level of Bloom's taxonomy. So given data is, the copper is a FCC structure, that is face centered cubic structure with atomic radius R is equals to 0.1278 nanometers. So it is equals to, that is atomic radius R is equals to 0.1278 nanometers, and then planes are 111 and then 321 plane. So for these two planes, we have to calculate the D value. For these two planes, we want to calculate the interplanar spacing. So to calculate interplanar spacing D, so we want to know the A value. So that what is the relation between R and A in the FCC structure? So relation between R and A in FCC is R is equals to A by 2 root 2. So as we want to calculate A, so A is equals to 2 root 2 into R. So it is equals to 2 root 2 into 0.1278 nanometers. So A becomes 0.361 nanometers, that is equals to 3.61 angstroms, or 0.361 itself we can write so that we can mention in nanometers. So A is equals to 0.361 nanometers. So now we can calculate the interplanar spacing by using the formula D is equals to A by root of H square plus K square plus L square. So for the plane D11, A by root of A is 0.361 nanometer, so 1 square. So HKL, so 0.361 divided by root 3. So it is equals to 0.2086 nanometers. Next for the second plane, 321 plane, it is equals to 0.361, that is A value, root of 3 square plus 2 square plus 1 square. So 0.361 divided by root. So 0.361 root of 14. So this value is 0.0965 nanometers. So these are the interplanar spacing for the planes 111 and 321 planes. Next problem is applying level of taxonomy. So the problem is potassium chloride is a FCC crystal having density of 1980 kilogram per meter cube. If its molecular weight is 74.6, calculate the distance from one atom to the next atom of the same kind, and the distance between adjacent atoms. So given data is density. So density rho, that is equals to 1980 kilogram per meter cube. Molecular weight, that is M is equals to 74.6, and then we have to calculate a distance between atom to atom. Distance between atom to atom, same kind. Same kind of atoms. That is A. And then we need to find the distance between adjacent atoms. Distance between the adjacent atoms. So for this, the formula which we are going to use is A is equals to Nm by rho into Na whole power 1 by 3. Here, as we know that M we know, and Na is Avogadro's number. This is 6.023 into 10 power 26 kilogram per mole. And the density is given, molecular weight also given, and N is the number of atoms. So here they have given a clue, that is FCC structure. In the FCC structure, the number of atoms are 4. That is face-centered cubic crystal. So in the face-centered cubic crystal, it has 4 atoms. So FCC means that along with the center atom, there will be atoms placed at the each face. So here 6 faces having 6 atoms. So top, bottom, left, right, front and back, 6 atoms are being shared. So that here at the face center, so each atom shared with 2. So half of the atom is being placed at the each face. So that we are getting 3 plus 1 at the center of the cube. So that 3 plus 1 we are getting 4. So N is equals to 4. That is along with the center of the atom FCC structure, each face have atoms at the center of the each face. So in face centered cubic crystal, along with the center of the atom, there will be atoms at each face of the unit cell. So that atom is being shared with 2 unit cells. That is each face, that is the atom which is at the center of the face, each face is being shared with 2. So that each face having half of the atom. So half atom here, half atom is being in this unit cell and half atom is being with the other unit cell, that is adjacent unit cell. Likewise, in all the unit cells, in all the phases, each phase is being shared with, each atom is being shared with 2 unit cell. So that this unit cell have half of the atom. So this unit cell, each phase has half of the atom. So that the 6 phases. So 6 phases. So half atom is shared. So 2. So 3 atoms are there. And the center of the cube, there will be 1 atom. So that 3 plus 1, totally n is equals to 4. Number of atoms in the face-centered cubic crystal is 4. So that n is equals to 4 in this case. So A is equals to 4 into molecular weight is 74.6 divided by rho 1980 into Avogadro's number 6.023 into 10 power 26 whole power 1 by 3. So it is equals to 6.3 angstroms. This is A value. This is A, lattice parameter. That is distance from atom to atom of same kind in the potassium chloride crystal. That is KCl. Potassium chloride crystal. Distance of same kind of atoms. So for adjacent atom, for the adjacent atom, we'll take A by 2. So that is equals to 6.3 divided by 2, 3.15 angstroms. So because, so for the same kind, the atoms have the distance A. So for the same kind of atoms in potassium chloride crystal, the distance is A. So that A is 6.3 angstroms. Where for adjacent atom, so for the adjacent atom here, so the distance between adjacent atom is A by 2. A by 2. So that's why 6.3 by 2 is equals to 3.15 angstroms. So the structure says that potassium atoms and also chlorine atoms. So same kind in the sense, we'll take A value, and adjacent means that we have to take A by 2. So adjacent means that different atoms will be different atoms being there. So between two different atoms, so the adjacent one is potassium with chlorine. So potassium atom with chlorine atom. So that is distance A by 2. So that A by 2 is equals to 3.15 angstroms. So the references are Engineering Physics by K. Tyagarajan, McGraw Education Private Limited, New Delhi. A textbook of Engineering Physics by M.N. Avthanulu, P.G. Kshiresagar, S. Chand and Company, New Delhi. Engineering Physics by Dr. M. Armugam, Anuradha Publications, Chennai, 6,17,000. Engineering Physics by P.K. Palanisamy, 4th edition, Scitech Publications, India Private Limited, Chennai, 6,07,000. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.